Hello everyone, this is the first video in a series of video tutorials that I'm going to record for developing a hydrological model from scratch using Python and only open source packages. This tutorial is a part of the HySetter project. HySetter is an open source Python package that I developed with support from Quasi through their Hydroinformatics Innovation Fellowship Program. So I highly recommend checking this program and applying for it. Next, let's go over some of the basic stuff, some of the logistics. I'm going to assume that you already have some knowledge of Python programming, so I'm not going to go over the basics of Python programming. I assume you know how to write functions and all that, what are the different data types. And the same goes for the hydrological modeling. I'm going to assume that you have some knowledge in hydrology and what are different concepts in programming, precipitation, potential of transpiration. So I'm not going to go over the technical details. I'm just assuming that you already have some knowledge of that. With the logistics out of the way, let's just start by talking about what is the HySetter project and then go over the details of the model. Before that, let me just recap the overall story that we are going to go over throughout all the tutorials. So in the first video, I'm going to go over the details of the hydrological model that we are going to develop, talk about the equations and the required input data, and then we are going to go over how we can use HySetter project to retrieve the required data. And then in the next video, we are going to go over the model development itself, how we can write those functions to run the model, and then do some analysis, calibration, and sensitivity analysis. So those will be for the next part of the video. Let's just start by HySetter. HySetter is built on top of the HyRiver software stack. HyRiver provides access to many data sets from various data sources that are related to hydrology and climatology, so hydroclimate data. And it uses web services to retrieve the data that are needed for areas of interest. And the HySetter is an abstraction layer on top of HyRiver and provides a command line interface as well as a Python API. That makes it very easy for users for novice and also experienced users to get the data quickly by just providing a configuration file. So that's the main idea behind HySetter. We are going to go over some of the details of HySetter throughout this tutorial, especially the first video. But now let's go over the model itself and see what are the required data for this model. So for this series of tutorials, I am going to develop a lump model. I might do another tutorial series on a gridded version, but for now we are only focusing on lump model. So with the lump model, we are going to assume that our control volume is a single watershed. So we need to aggregate all the properties and especially gridded data like forcing onto the watershed itself. So so we are going to assume that the watershed has representative values. All right. Now let's see what is the model itself. So the NCRS-PDM model, I provided the paper for this here, so you can just click on it and you're going to be redirected to the paper, and you can go over the details of the model itself. But here I'm just going to briefly mention some of the basic idea behind the model and what are the equations, and so we can see what are the data that we need for this model. So this is a figure from the paper. As you can see, this part is the runoff generation, and then the second part is for runoff routing. So for the runoff generation part, we see here that we have this R stands for runoff, which is a total runoff, which is meaning that sum of subsurface and surface runoff. This W is wetting. So this W is computed from here. You can see here that is using that there's a the wetting is computed using a probability distribution function. You can go over the details of why this. You can from the paper. You can read more on the probability distribution function that this model uses. But the basic idea is that we are by using this probability distribution function, we are going to have soil storage heterogeneity over the watershed area. So by computing this W and subtracting from the total precipitation, we can compute the runoff. Essentially, this equation that you see here. Oh, sorry. So this equation, let me undo this. So this equation, which is, if I can create, let me just make it easier. Right. So this equation is the difference between the precipitation and wetting is going to give us the total runoff. Next is the runoff routing, which is going to be the second part of this graph. As you can see here, that the total runoff is divided into direct flow and groundwater, or for the base flow essentially. So for the surface flow, it's going to go to one storage tank, which we call quick storage tank, and then the subsurface runoff is going to go to this low tank, which we call here is a groundwater tank, right? So SG is for groundwater, D is for direct flow. And then the output of this tank that we compute from a linear storage equation, we are going to get the stream, or we're going to get the direct runoff. We're going to get a direct flow and the base flow, right? So this QD and then QB. So far we have this parameter, this gamma, which is the coefficient that is going to divide the total runoff into surface, subsurface. And then we have this residence time parameter for the storage tank to convert the runoff into flow, into stream flow essentially. And then the sum of the direct and base flow is going to be the total stream flow at the outlet of the watershed. So the equations for the runoff generation, for the runoff routing, are going to be relatively simple. Linear storage, so we have this KB, which is 1/day. Essentially, if we divide the storage by this residence time, we can get the outflow from a tank. So the model itself in the paper assumes that there is one storage tank for the slow and one is for the fast flow. But in the implementation, we are going to modify this slightly, and we're going to talk about it later on. We're going to use the Nash cascading model, Nash cascading concept. Now that we have our runoff generation and routing, we need to close the system by adding a water balance equation. So for the water balance equation, we need to compute the actual evapotranspiration. So in the paper, they introduce this equation for computing the actual evapotranspiration. And then once we have the actual evapotranspiration, the difference between the total precipitation and the actual transpiration is essentially the only abstraction here we have is the actual evapotranspiration. So this component is going to be our source term. And then for the water balance, the changes in the storage is going to be the inflow minus outflow plus the source term. So the inflow in this case, because we are modeling head watersheds, the inflow is going to be 0 since there is no upstream watershed. Q in is going to be 0, and Q out is going to be is the sum of the direct and base flow. And once we have the changes, then we can compute the storage for the new time step as a sum of the essentially excuse me, is going to be we're going to add or subtract from the previous storage. Delta S can be negative or positive. So the parameters that we have, as I've mentioned, there is one soil storage capacity, and then a shape factor, which varies from 0 to 2. Sorry, the water storage is going to vary from 5 centimeters to 2 meters, and then the shape factor from 0 to 2. The gamma is from 0 to 1, which is a partitioning factor. And then for the residence time, which is 1 over day, is going to vary for the base flow for the groundwater from 0 to 0.14, which is essentially around 7 days. So more than 7 days is going to be a value for residence time, and then less than 7 days is going to be residence time for the quick storage tank. Just to give you a visual representation of the workflow that we have in mind, in this case, we're going to modify the model structure comparing to the paper slightly by adding a snow module, because we are going to simulate a watershed that has a snow. So we are going to divide the total precipitation into snow and then rainfall, and we're going to have one storage for the snow. So this storage is going to receive a snow and then pass liquid water as a snow melt, and then a part of precipitation is going to be rainfall as well. So we have a snow melt, and rainfall is going to give us the liquid, the total liquid that enter in the soil. And then from soil, we are going to have these two kind of quick and slow that we talked about, and then finally the stream flow at the outlet watershed. So what's important to note here is that we have 4 different storage tanks that we need to keep track of for the water balance equation. If you recall here, we have this water balance equation, that this water balance equation applies to each one of these storage tanks. So that's what I want you to take out from this figure, that we have these 4 and we need to make sure to keep track of them separately. And then as a whole, just 4 of these should satisfy the water balance equation. This is one of the most important aspects of hydrological modeling, just to make sure that the water balance is preserved. We'll go over more details how we can check for this, but for now, let's move on to the next part. So the next part is the data retrieval. As we can see here, let's go over what do we need. So for developing this model, you can see here that the inputs are precipitation. The inputs are precipitation, and then we have also potential evapotranspiration. So for computing the actual evapotranspiration, we also need the potential evapotranspiration. So these two are the 2 forcing data that we need. And as I've mentioned, we are going to also we are going to need to compute the snow. And for the snow, we also need temperature, minimum temperature to be precise, because we are going to use a relatively simple model for the snow. So the required forcing are precipitation, potential evapotranspiration, and temperature. Now, let's see what are the data that we need. These are some of the packages that we need, and in order to install everything that we need for this project, I would recommend using Pixie. So I'm going to assume that you have some knowledge we're working with a terminal, so I'm not going to go over the details of that, but I'm going to provide the link to all the files that you would need in order to follow along with this project. So for this tutorial, I provided this notebook that is available from the HySetter project. You can just clone the repository. I'm going to put the link in the description. So you just need to clone the repository using Git. And then once you clone it, you just change the directory cd to the newly kind of cloned repository, and then you would have access to all the required files for this notebook, for this tutorial. So once you cd to the root of this directory, then I would recommend installing Pixie. I would also add a link to the in the description. I'm going to add a link to the Pixie software, so you can easily install it, whether you're on Windows or Linux on Mac. You should be able to easily install Pixie. And then once you have it installed, the only thing that you would need is to just run pixie install edev. So once you run this command, it's going to install everything that you will need for this project. And then once you install that, here I'm using VS Code as my IDE. You can use Jupyter Lab or whatever, PyCharm, whatever you're using. But in this case, I'm using VS Code, so the instructions are going to be related to VS Code. You can adjust it based on your whatever IDE that you're using. So in VS Code, once you open the tutorial notebook, which is under docs, examples, and then there's this NCRS-PDM notebook. So if you open it and then click on the Jupyter kernel, then you can select the dev environment, because essentially what this command does, this pixie install edev, is going to install a new environment called dev. So now we need to load this as a kernel to run this Jupyter notebook. So it's as easy as that. You don't need to do anything else. That's why Pixie is very kind of easy to use. All right, so now the first step is just we need to import the required packages. We need GeoPandas to read in the data sets that we get from HySetter. And then we also use Numpy. All the kind of the core solver is going to be using Numpy and Numba, and pandas, also an X-array. So these are your typical geospatial packages that you would need. Additionally, we're going to use PyGeoHydro from HyRiver. There are some kind of helper functions that we would need to use, that we're going to use PyGeoHydro, and also Hydro Signatures is another HyRiver package that we are going to use. So these two packages are needed. All right, and then the HySetter itself, as you can see here, as I've mentioned, HySetter has a command line interface as well as a Python API. So for the Python API, the only thing that you would need from HySetter is this config object. The rest, everything else is under this kind of class. It has all the kind of attributes that you can use to access the files. So from HySetter, we import this config class, and next, if you're using the command line interface of HySetter, you would need to provide configuration, a YAML file as a configuration file. Or if you're using the Python API, you can create a dictionary with all the required config files. So what are the required inputs? There are two mandatory fields for HySetter config. One is project and area of interest, AOI. The rest, there are several data sets, and the rest are optional, but these two are mandatory. So for the project, you will need to specify the name of the project, can be anything. I would recommend against kind of using spaces or special characters, use underscore or dash or something like that. But for the data directory, again, you can specify any directory, and then everything is going to be created for you. So you don't have to actually create this, whatever the name you specify. So in this case, I'm using data, which is going to be created in the current directory. And then for AOI, there are different options. I would recommend going through the documentation of HySetter to see what are the available options. We are going to be seeing just only a limited number of configurations. So you can check out the documentation to see what are the other datasets that are supported. So for the area of interest, one of the options that exist is gauges 2 basins. So from the gauges 2 datasets, we can specify the name of the IDs of the USGS stations. You can specify as many as you like. The HySetter is going to get all the data for these stations. Essentially, these are the areas of interest. And then we can also get some attributes. For example, in this case, we're going to get the attributes from StreamCat datasets provided by EPA. However, for the LUMP version, we are not going to be using the StreamCat, but I will probably make a gridded version tutorial later on that we are going to use this StreamCat. So the wetness index, topography wetness index, and BFI, and the rest. So you can specify as many attributes as you like. Next, we are going to be using, we're going to get the forcing data. There are, this HySetter supports 3 data sources for forcing: GridMet, DayMet, and NLS2. In this case, we are going to use GridMet, which has a resolution of 4 kilometers, and the start date we use 2000 to 2020, so 20 years. And then the variable name depends on the of the source. So for GridMet, we want the precipitation, potential transpiration, and minimum temperature. So these are the names. For DayMet and NLS2, the names would be different. And for another thing related to the configuration of HySetter is that for the gridded data sets such as forcing, soil, topo, and NLCD, for all of them, there are 2 additional options. One is crop and another one is geometry buffer. So for the gridded data, you can specify that whether you want to crop the gridded data on using the geometry of your areas of interest, right? So here, this AOI can be a complex geometry, right? So, but you can specify that the forcing will be downloaded for the bounding box of that geometry and will not be clipped by the geometry itself. Another option, which is a geometry buffer, essentially what this does is just going to buffer the geometry before retrieving the data. These 2 can be very helpful. For example, for the topography data where you want to kind of do some geospatial operations such as watershed boundary delineation or flow accumulation. For those, the boundaries, what's happening at the boundaries could be important. So that's why these 2 options are provided. So we make sure that we get some extra data and then we clip them manually after the post-processing operations. All right, so, and then for the soil data, there are several sources. It can be GNAT-SG or Polaris. Polaris is a seamless soil data across CONUS and has several variables at different depth from 5 centimeters to 2 meters. And then the variables that we need in this case for this model is buck density. We're going to talk about why do we need it later on after the sensitivity analysis. So the soil data is needed in this case. And then we also going to be taking a look at the NLCD, the land use, land cover, and canopy. Again, canopy, we're not going to use it in the lump model. In the gridded version, we might use it. But for the lump model, we're not going to be using canopy. But for the cover, for the land use, land cover, we want to make sure that the watershed is natural and does not contain urban components. So that's why we're going to get the covered land use, land cover. And you would also need to specify the year. Can be different number of years. You can use different 2016, 19, different years. But in this case, we're going to get the data for 2016 because the start and end date is from 2000 for 2019. So we want to get somewhere in between these values to get the land cover. And then lastly, for calibration, we need to get the streamflow observations. Again, with the same dates that we got for the forcing data, we're going to get the streamflow data at daily time scale because the forcing is at daily. GridMet and DayMet are at daily, but NL-2 is at hourly. So because we are using GridMet, so it's going to be daily. And then you also need to specify which USGS station you want to get the streamflow observations from. In this case, we are going to use the use call option. Essentially, we are going to say that use this column called gauge ID from the gauges 2 basins data sets to get the USGS station number. You can either directly specify the number here, the USGS stations, or you can use this use call. So now that we have this dictionary containing everything that we need, we just need to easily just pass this dictionary into the config object from HySetter. Once you do, then it has a couple of methods and attributes that we need for accessing the data files. So the first step is that we want to get the data. So we use this method called get data from this config object. And once you run this, it's going to essentially, let's run this. It's going to get the data, all the data. You can see that it ran pretty fast. And the reason for that is that I've already run this project. So, and if the files exist, it's not going to re-download the file. So essentially, it's just going to get the data that hasn't been retrieved already. So for you, if this is your first time, it's probably going to take some time to run. But once you run this and get all the data, then everything is going to be saved in the directory that you specified on your project. So the directory is going to be data, whatever you specify, and then the name. So data and then NCRS-PDM. You can see here that once I ran this, so there is this data here on this side and then NRCS. You can see here that all the data that we requested are downloaded here. So if you use the command line interface of HySetter, then you would need to go over this data and check the data structure and see what files are downloaded and where they are. But however, the Python interface provides a much convenient way of accessing the data. The paths to all this data that have been downloaded, and it's by using this file path attribute of the config. So the config has this attribute that under this attribute there is you have access to all the paths. So for example, let's just see what is this. So you can see here that let's check this file path object itself. You can see here that this file path object contains the project the root, the root of the project, and then for different data sets that have been processed. So this AOI, area of interest, parquet, and then flow lines, stream cat, I don't know, like others, soil, NLCD, topo. So you can see here that you can access different objects. For example, topo. You see here that this topo object is a list, is a file object, is a custom data structure that is based on a list, but essentially it's a list. So, and the first item in the list is going to be associated with the first item in your area of interest, right? So if you read in the area of interest Parquet file, you can see here that the first index, whatever the 0 index, is going to be this geometry associated with this gauge ID. And then for all these objects under file path, the first path is going to be associated with the first gauge ID. And then the second one, which is 1, is going to be associated with the second USGS ID. So this makes it very easy to get the data for whatever, to get the path to the files that have been downloaded. All right. So now that we have our geometry, let's check it. Let's focus on the first one. Essentially, the first gauge ID, the first USGS station. So we read this. We want to get the area. Just check what is the total area in a square kilometer, in a square meters, because for aggregating all the parameters and conversion to cubic meter per second, we are going to be needing this area. So we compute the area by just reprojecting the geometry, the basin geometry, into 5070, essentially converted into a projected CRS, which is in meters. 5070 is in meters. So the area is going to be around 4,000 square kilometers. So you can see here that it's a relatively large watershed. For lump models, usually the area, the watershed area is supposed to be around 500 to use a lump model safely. However, in this case, because we are going to also later on develop a gridded version, so I selected this larger station so we can compare adding complexity as a gridded version if it helps with more accurate modeling of this watershed. So for the lump version, although it's 4,000 kilometers, still we are going to use it and see how does it work in this case. Now that we have the area, now let's check the land cover and see what is the land cover for this watershed. You can see here that for the NLCD type, for the NLCD dataset, we didn't specify crop. Crop by default is set to true, and the geometry buffer is by default 0, right? So in this geometry buffer, just if I missed it before, is in meters. So this 8,000 is 8 kilometers. So for NLCD, because we didn't specify crop and geometry buffer, is going to clip the data into the geometry. So we see here that if we just read in the NLCD, get the NLCD path from the file path object, then and read it using X-array, we can plot the land use land cover using X-array. Another utility here that we're going to use from HyRiver, from PyGeoHydro package, is that it provides a function called cover legends. These are the official land cover, essentially color map and levels, which are the values of the land covers. So 11, 12, 21 up to 95. So these are the land cover types. And if we don't know what are they corresponding to, then PyGeoHydro provides another helpful function called NLCD helper that provides you with the names that are associated with each one of these land cover values. So for example, if we take a look at the plot, we see here that mostly 41 and 43, 41 and 42 are the dominant types, and 43, so 40, 41 and 2 and 3 are the dominant types. And if we take, you can see that these are 4 different forest types. So 41, which is the dominant, so deciduous forest, is the one that is the dominated area. So we see here that we can see visually that this watershed is mostly natural. However, we see here that there are some red land cover types, which are 23 and 24. And if we check from here, we see here that 21 to 24, these are related to urban areas. So let's get the percentage of urban area. In this case, we can use the land cover type. We can use the cover data set and then use the easing method from X-ray and find all the cells that their file type is 21 and 20 to 24, and then divide by the total number of cells that are not null, that are not NaN essentially. And then we take the ratio of these two. We see here that it's around 2% is urbanized. So which we can safely assume that it's a natural watershed. Now that we have the data that we need, we want to also add the forcing data, right? So let's just start by importing the forcing data again with the same pattern as before. We use from the file paths object, we use the forcing, and then the first one, which is associated with the first watershed. Again, we are going to read it with X-ray. The only option comparing to the land cover is that we are also providing this decode codes and all, because we want to use Rio X-ray to clip the data. Because if you remember the forcing, we set the crop to false. So we need to manually clip the data into the boundary of the geometry. So we specify that. And then another thing, Rio X-ray by default assumes that the name of the spatial dimensions are X and Y, although you can change it with Rio X-ray, but here we're just going to, for simplicity, we're just going to rename the data to X and Y. So rename the latitude and longitude to Y and X, and then PR to precipitation and TMMN to Tmean to make it a little bit easier to see what do they represent. Another thing we need to do is that that GridMet provides temperature in Kelvin, so we need to convert it into Celsius, degree Celsius. We just need to subtract it by 273.15 to get the degree in Celsius. And then, as if you recall, we need to also compute the snow. We are going to use a relatively simple method to compute the snow. That I provided a link to the paper. You can easily just go to the paper and take a look at the methodology there. But the main idea is that we have 2 temperature thresholds, rain and snow. If the temperature is above rain, it is above this temperature, which is 2.5 Celsius and 0.6 Celsius. If the temperature is above this threshold, precipitation is going to be rain. If minimum temperature is below this T snow threshold, precipitation is going to be fully snow. And if it's between, it's going to be proportional, depending on the temperature that is between these two values. So we can separate snow and rain from the total precipitation. Now that we have precipitation, temperature, minimum air temperature, and also the snow, now we need to clip the data, as I've mentioned, because crop was false. So we use this Rio accessor and then use the clip function in order to clip it to the geometry. The other thing that I want to note here is that I specified alt touch as true because we want to make sure that at the edges of the boundary we also have cells. So alt touch was set to true. Now that we have a snow computed, we want to make sure that the snow is dominant or not. So we are going to compute the snow fraction, which is essentially we are going to resample, compute the annual average of a snow and total precipitation and take the ratio. So the ratio of the snow over total precipitation, the annual average, and then another average, just to make sure that we get it for the 20 years. Within that 20 years period, we see here that the temperature, that the snow fraction is the snow percentage is 44%. So which is not negligible. Usually if it's less than 10%, we can safely neglect the snow, but in this case it's definitely more than 40%. So we need to have a snow module. Then for the also calibration, we need to have the streamflow data. So for the Q observation, again, we use the same pattern from file path, get a streamflow, get the first one, and then read it with X-ray. So the streamflow are downloaded as an X-ray and saved as an X-ray file. So you have, for all the stations, you have access to some of the attributes of those stations as well as the time series. So what we want to do is that we want to convert this into a pandas data frame. So we just select that and then convert it into pandas data frame. And also this is, we have our forcing, and now we have our Q observation. And now we are ready to move on to the model development itself. So with this will be the end of the first part of the tutorial. We went over the details of the model equations and the data that we need. And then we used HySetter to download the data. And then we looked at how we can access the downloaded data and do some post-processing operation, making sure that everything is ready for the next step. So if you have any questions, feel free to ask and add comments. And I would recommend checking out the documentation of HySetter if you have more questions about HySetter. And then for the next part, we are going to go over the model development aspect of this tutorial. So see you next time.